we were here with we were here defining different operations that we can do to display images, and this is simply just an indication that you can be very creative when you want to display some information. So you should look for the display or for the way to show the data that maximally convey the information that you want to transmit. So, for instance, here, scaling between minimum and maximum is a good idea, but it seems that it doesn't show very small differences. The problem is that there is a, let's say, but we will see later what is a histogram, so we don't have yet the concept of histogram for the moment. So let's say that this pixel here has a very high value, all the rest are small, and then when you scale between minimum and maximum, this one dominates, and then all the rest become very dark. So maybe for this particular image, this scaling is not very good. So let's look for something else, and then this something else could be a logarithm, could be d squared or whatever. So yeah, again, something is the information content of an image, something else is how to display that information content. Okay, next. Yeah, this is something of MATLAB that this year we don't care so much. There is something interesting in this MATLAB notation. That is, okay, so let's say that you have an image, and you can index that image in many different ways. So let's go to whiteboard. Okay, so let's say that we have an image. So we have it. So let's say this is 1, 4. Whether starting at 0 or 1, you know, it is a matter of languages. So C languages, Java, Python, they like to start at 0. MATLAB like starting at 1. But okay, let's start at 0. So these are the rows, these are the columns, and then we have I, RC. But you can construct, for instance, let's say that I want to refer to this particular pixel. So that particular pixel would be I of 2, 4. Okay, very easy. And if I want to go for all pixels, ¿por qué non ci Anna? ¿Por qué non ci
No sé.
Bueno, sabes, ha venido ahí por el camino pensando.
Sí. ¿Dónde se queda en el medio? Sí.
That is the most famous joke in Spain, at least. Okay, so we have, let's say that I want to construct a new image. So if I want to construct a new image, I may, for instance, do something like that. So say, for instance, my new image at the location RC of the new image is let's make it red, is I at the location 2R to C. Okay, so now we have a new image. Let's make it smaller. So I will have a new image. And in the new image, I have 0, 1, 2, 0, 1, 2. And then I of 0, 0 is equal to I of 0, 0. And then that means that this pixel here is coming from there. Okay, what happens at I01? I01, this is coming from I02. So that means that this pixel here is coming from there. And so on. So this one is coming from here. And yeah, and the same for the rest. Okay, this is something that you have already done in 1D signals. So in 1D signals, you are used to this kind of transformations. So for instance, you say x of n is equal to some other x prime at 2n, for instance. So that is what we are doing, or the same for t. So x of t is x prime to t. And scalar transformations are not the only ones. In general, you can put there any transformation that you like. So you can put any function phi that transforms coordinates or arguments in one of the functions in coordinates of the other function. Okay, so actually we will at some moment we will expand that idea quite a lot. This is what we call in the first presentation we call it, let's make it blue again. These functions phi called a warping. A warping is a geometrical transformation. So in this geometrical transformation, this one is particularly simple. It is just this operation here is called decimation. Decimation. The name comes from skipping 1 every 10. That is the decimation. This is 10. But otherwise, it can be used with any arbitrary scheme, so or any arbitrary gap. So here our decimation is by a factor 2. And we will see, or it is also called downsampling. I will also refer to it as downsampling. So you have some sample signal, and then you downsample it by decimating and taking 1 every 2, 1 every 3 coordinates. Okay, then let's move on a bit. Okay, so here we have by a decimation by factor n. So you are going, and this is just the notation in MATLAB. We don't care about MATLAB, but the idea is interesting. I can go from 1 to the number of columns in steps of n. So I go in steps of 2. I went in steps of 2 in my blue image before in the example. And here we have an example in which we are going in steps of 3. So we are taking this line and then skipping to another line. Potremmo citarlo, Anna?
¿Cuál es la diferencia entre un volcán y un terremoto? El terremoto ensucia y el volcán no.
Then you may apply again. Your function phi can be any function phi. So for instance, your function phi that transforms coordinates from one image to the other may skip 2 rows. So 2 rows every 3, but may not skip any column, for instance. And the same for columns. So you may skip columns, but not rows, and you can construct whatever function phi that transforms coordinates from one image to the other. And even you can skip in both, and then you would be doing the decimation that I did with the blue image. And yeah, this is just another representation of the same thing. So highlighting which pixels will be taken from the original image. But you can construct functions, phi functions, that do not even respect the spatial order. Okay, so a spatial order means if you have a pixel and you have one sample on the left and another one on the right, and those 2 pixels, left and right, are kept in the new image. One is at the left of the other. Okay, but you may not even respect that. So for instance, let's say that your function phi is taking columns 5, 11, 28, 25, and in that order. So 28 and 25, they are reversed, and 19 and 14, they should be before 28 and 25. So you're not respecting the order. And the same for the rows. And then you would be taking these pixels, this pixel, this pixel, this pixel, and rearrange them in this pattern. So for instance, you would take, the first one would be 5, 10. The second one in this direction would be, let's keep first, sorry, 10 is here. So it would be 10, 5. The second one would be 10, 11. So this one. The third one, 10, 20. So it is this one. But you are taking as the third pixel. Okay. And the same for all the rest. Okay. So yeah, this is just a highlight of how they are taken. Okay. So let's. So for instance, if you do it for a particular image, that is what you get. And here you have an extreme case of that. Okay, so let's say that our image is of size 576 times 768. So this is a width and height. And then your function phi is just a random permutation. So it is just scrambling all the numbers from 0 to height and from 0 to width, and you reorder them completely arbitrarily. And now you access those pixels in disorder. Okay, so you follow this pattern. So you simply follow the rules that tells you the function phi. So the function phi tells you which pixels you have to take every time. And we saw it here in this example. So for instance, if this is my transformation, I have to take first 10, 5, and then 10, 11, and then 10, 28. And when I finish with this row, I will go with 7, 5, 7, 11, 7, 28, and so on. So you do that. And you construct a new blue image, as I did before on the whiteboard, following this pattern. And this is what you get. This is what you get. Okay, so you have completely destroyed the original image. And here it comes something that yesterday appeared a couple of times. So when are you losing information? Okay, so let's think of something. Okay, so let's say I have a function. Let's make it with images. So let's make that. So I have a new image, I prime, that will be some function. And for instance, let's start with something easy. So let's say I simply take another image, I of t, multiplied by 2, and let's keep for the moment the range, let's keep it real, so that we don't have problems of 0 to 255 multiplied by 2 and so on. Okay, so we have real images. I have a real image multiplied by 2, and I have a new image. Okay, so have I lost any information? Yes? The information contained in this image is exactly the same as the information there. No. Why not?
You say half.
Because?
You lose half of the information.
You lose half of the information. Okay. So let's say that you see in the blue image, you see a value, I don't know, 129. What was the original value here? 64.8, 64.5. They are real images, so you are not rounding. So you have exactly the same information. What does it mean to lose information or to not lose any information? It means that if I want, I can recover the original image simply by dividing by half. And then I have exactly the same information. So actually, let's generalize this. So if I have an image, and it is some transformation of some other image, sorry, I don't like this. So I don't lose information if this function f is invertible in that domain. Okay, so and this idea of in that domain is important, and we'll come to that now. So I of t is f minus 1, so it is the inverse of I prime. So I don't lose information if f minus 1 is invertible. Okay, so in that domain, it means, let's say, I said before, okay, let's say that the images are real, so I don't lose information, because if I see 129, that means that the original image was 64.5. But let's say that my images are not real, they are 8-bit unsigned integers. Okay, so if I see 129, I don't know if, yeah, let's make it the opposite. Okay, so it doesn't apply to this example. In this example, there is no doubt, because I would never have this value. But let's say that I have here the value. I have here the value 64. I have the value 64, and my transformation is I prime is 1/2 of I. Okay, so if I have that my new image is 1/2 of I of t, and I see 64, I don't know if the original image. Quando non ci nada.
Sí.
Cuando no algo. Claro. El que llega tarde con noche.
A ver. Vale. Es un gangoso. ¿Sabéis lo que es un gangoso? Vale, pues un gangoso que va a una heladería y le dice al dependiente, o sea, al que trabaja ahí, que no, un yogur. Entonces le dice el otro, Danone, y dice, Danone más de la nevera.
Muy bien. I promise you that this system is effective. So at the end of the year, of the course, no one is late. Okay, so if I see 64 here, I don't know if the original value was 128 or 129, because in my range of unsigned integers of 8 bits, this function, this transformation is not invertible. So I have lost information. Okay? So you don't lose information if your transformation is invertible. And you lose information if your transformation is not invertible. Okay, so regarding the scrambling, that is a transformation. Actually, geometrical transformations, they also respond to this scheme. So this scheme is absolutely general. So a function f could be, so for instance, for geometrical transformations, could be I evaluated as some other function. I'm using t, these are images, so I should be using vectors. Okay, so the function f could be this one. How to invert that? So I can invert it. So let's make it more clear with colors. So this is the image that you are interpolating. So you can invert that function. I want to get I again. So you are given I prime. You want to get I again. So I at t is I prime. I prime at 5 minus 1. So we have a scramble, we have an image. We have a scramble it and takes out an image. If that transformation is invertible, you have not lost information. So the scramble image, have we lost information? As long as you keep the random permutations, you have not lost information. So here you see that this is the red image, this is the one on which we are applying phi. We are constructing a blue image. This is the blue. Is it invertible? It is. It is. You simply have to take the blue image and take every pixel and put it in the right place in the original location. So as long as you keep the random permutation, the information is not lost, so you can recover. Okay, so yesterday it appeared a few times, have we lost information? Have we not lost information? So as long as transformations are invertible, you haven't lost information. And let's look at the transformations that we had yesterday, where we made these comments. Okay, so for instance, the first one was this scaling transformation. The scaling transformation is invertible. Let's look at it. So we had here I, we had I prime, and we're mapping M capital M to M prime capital M prime. That was this line. Okay, so if you are given a value, of I prime, can you recover I? I can. What I have to do is to go to here and then go to there, and I have I. So if you give me some I prime, I automatically can compute I. So I have not in the real world, not in the integers or unsigned AB. And in the real world, in the real numbers, I have not lost information. Okay, so let's look at some other. Okay, there was another transformation. So this is a scaling, except for the quantization. The quantization is losing information. But except for the quantization, the scaling is not losing information. What about the logarithm? The logarithm is this function. It was logarithm of t plus 1. So it is logarithm of I plus 1. So it is this function. And again, this is, if you give me I prime, I can compute I. So again, I'm not losing information in the real world. There was another one. That was this square. Okay, this square. What happens with this square? So I have let's have more space. So I, we have I prime, is I squared. It is this function. And now you give me one value here. What is I? You don't know. There are two possible i's. One is this, the other one is that one. So this could be a possible I. This could be another possible I. So I don't know which one of the two. So this transformation is losing information. So when I said we are not losing information, it is just a display. Yes and no. It is true for this two. It is not true for this one. Except for the quantization. But the quantization is just a small term. But this one is losing significantly part of the information. Okay, so let's see some other functions that are very common in this context. So it is very common to construct functions like this. So I prime is the maximum of 0I. So that function is like this. So let's make it clear. So it is like this. Always that you make a drawing, always put the labels. If you don't put the labels, that drawing doesn't mean anything. Okay, that plot doesn't mean anything. Okay, so this is the function. Have we lost information? Do we lose information for that function? We do. If you see a 0, so if you see that I prime is 0 here, you don't know which one of all these i's they give 0 in I prime. Now our images are real, so they can take positive and negative values. Okay, so actually this transformation is very famous one. It's called RELU. And this comes from rectifier lookup table. And it resembles a bit the response of which device. What is an electronic device that has that response? I make the drawing. What is that? A diode. This is a diode. You see, everything is connected. So this is a very much used in transformation, especially in deep learning. In deep learning, they use a lot of this transformation. Okay, so very interesting ideas. So I can transform images, and as long as I'm not losing much, I'm not losing anything at all, as long as the transformation is invertible. And they can be as weird as this one, and it doesn't matter. If I can invert the transformation, I can recover the original signal. Okay, good. Questions? Yeah.
I don't understand why the last transformation is
Okay.
It's not invertible.
That one is not invertible because of this one. You see that I prime is 0. You don't know which one of these i's it is. All these i's, they give 0 in I prime. Okay. Any other question? No? Okay. Then next lecture is about histograms. So histograms, I'm sure that you have heard this in biostatistics or things like that, no? Have you? It is not the first time that you encounter a histogram. So histogram is just a count of how often you have seen a particular value. So for instance, let's say that our images are from 0 to 255, and then you are given this image, and then you count how many times I have seen 0 here in this matrix, how many times I have seen 1, 2, 3, 4, up to 255, and you make a plot with those counts. Okay, so for instance, this image, it is very dark, so we would expect that the dark values, so this is black, this is white, so we would expect that the dark values have a lot of counts, and that is what's happening. So most of the histogram is concentrated around the dark values. Okay, what about this one? So this one, well, it is much brighter than before, so we should see counts moving to the brighter part, and that is what's happening. And actually, we see here in the histogram, we see two different regions. So we see a region with a lot of counts, and then, okay, much less, and then again a lot of counts. So that tells you that you have two regions in the image. Actually, if you want to be even more subtle, you could have three regions. You could have 1, 2, and 3. So what are the three regions? So when you look at the image, for instance, what is this bright region? The sky. So the sky is brighter than the rest. Okay, so what is the second region?
The trees or the background?
The
Background?
the background, the ground.
No, the background. What is behind the trees?
Behind the trees, this one.
Yeah.
Yeah, it could be that one too. I would say it is the ground. But I'm not sure which one of these two is brighter. Maybe the tree. And what is this third region? Sorry, the tree and the ground. Okay. Yeah, so the same idea now. Yeah, that is an interesting feature of this histogram. That is, it is not fully utilizing the range of the image. So it could have taken values from 0 to 70, but it doesn't take any. So there is no number here in this matrix. That is 10, for instance. So there are 0 tens in this image. The same on the other side. And on the other side, there is no number in this image that is 250. We have 0 pixels with 150. So that means that even if you are allowed to use numbers from 0 to 250 or 55, you're not using all of them. So that means that you're not fully utilizing your range. And we said yesterday that the contrast is the difference between minimum and maximum. So somehow in your image, your minimum and maximum are closer than they could be. You could expand this later and we know the scaling operator already. So we could use the scaling operator to increase the contrast of this image, as we did yesterday with the threads. Okay. Now this one. Okay, so they have the histogram is there is nothing new in the histogram. There is one feature that is new. The sharp count here, it doesn't look natural. Okay, so let's look at natural histograms. So natural histograms, this one falls very quickly, but you see that it is falling. This one, it rises very quickly, but again, you see that it is rising. But this one here, falling. This cut, you see? So what is it? How do you call that?
In Spanish is that spur?
Also,
The image is blurred.
yeah. So in Spanish you say quemada. It is saturated. It is saturated. Your sensor is saturated. So your sensor transforms voltages at the end. So it has a voltage. So whatever number of photons is arriving, photons are translated into electric currents, and at the end you have some voltage. So your voltage is saturated, so you cannot represent something higher than a particular voltage. And beyond a given point, you are simply giving your maximum. Okay, so the maximum is 255, and this image, for instance, some of the pixels are saturated. They are giving too much light to the sensor, and the sensor cannot encode a number larger than 255, and it is simply cutting. It is giving you the maximum it can. And what about color images? So in color images, we know now that we can decompose this into 3 components: the red, green, and blue, and then we could compute the histogram of each one of the channels independently. And then we already recognize these features of multiple regions and then saturated histogram. So the red channel is saturated. So some of these pixels, they have even more red light, but the sensor could not give more. And the same on the blue. So the blue was particularly low for some particular area. So there is saturation in both ways, in both sides. So either because something is very dark or because something is very bright. And actually that has to do with something that we normally don't think. That is, okay, so let's say that we plot here what is the response of a sensor to the input. Okay, so this will be input. That would be number of photons. And this will be output. This is for instance, in a camera will be some voltage in some transistors, and so let's say this voltage in our eye is the firing rate of the neurons, so that the neurons are firing at a given rate, so it will be firing rate. And we would like that this relationship, so depending if you receive 0 photons, you have a 0 current or a 0 firing rate. And if you have some photons, then the relationship is linear. That is what you would like, to have linear responses of your cameras and your sensors. What happens in reality is that, for instance, even for 0 photons, if we think of neurons, the response is not 0. You have some firing rate, so neurons are all the time firing, independently of whether they receive any input or not. Only that the basal firing rate is very low. And then, and the same happens with cameras and all that. They always have leakage currents and so on. And then, as the number of photons increases, so we would expect that this increases. And then at some point, what happens with most of the sensors is that they saturate. They cannot, for instance, in neurons, they cannot fire more quickly than a given frequency. And then your sensor is tuned to some region. So your sensor is tuned, for instance, you work in this linear region of your sensor. So this is the minimum for your sensor. This is the minimum and the maximum. And if you receive something smaller than the minimum, you saturate. And if you receive something larger than the maximum, you also saturate. And this happens with cameras, it happens with your eyes, it happens with all kinds of sensors. So there is a relationship between whatever you are measuring and the actual measure that the sensor is giving. And typically you would like to work in the linear region, that relationship. And you tune, there are actions that you do to shift this sensitivity. And you can decrease it as much as you like. So you can be very sensitive here, you can be, so you can, there are actions that you can do on your sensors to move this minimum and maximum that you can allow. And this is what we have seen in this image. So we see that the red sensor is saturated, the blue sensor is also saturated. And it can be saturated because it is receiving a lot of light or because it is receiving too little light. Okay. There are more funny things, like for instance, we see the sky here in the histogram. So this is the sky, in the blue histogram. And what about what is this? This large region in the blue histogram. Whatever is not the sky. So whatever is not the sky doesn't need blue. So the blue value will be relatively low. And then this is the paradigm. And the same happens with the rest of histograms. You can analyze what are the features of this image and how they are translated into histograms. So for instance, this part of the image is mostly red, and there are all kinds of reds. And this is what you see here. So that is all kinds of reds. Okay, good. And yeah, more examples. This image is mostly green. So that means that the green values, the high, so the large intensities, the green histogram is above the red and the blue histogram. And you don't need so many in blue or intense blue values. And then the blue histogram at high intensities, it is almost zero. So you can always map these features in the image to features in the histogram. Some other examples, more examples. So a lot of examples. Okay, so yeah, so what is a histogram? A histogram is another function. So when we compute a histogram, so let's say I have an image. Let's say I have an image that I will not write the arguments. So this image takes values from, let's say, z squared. So we have pixels, so discrete pixels, and we go from 0 to 255. 0 to 255. And you know that when I use curly brackets, it is because it is a discrete set. And now we have an operator that takes an image and produces something. So, okay, so this operator, what is the output? Let's say that this is H, the histogram. So I will not write the operator because the operator, how to write the operator is a bit more complicated. But what is the output? So the output is something that goes, what is the range? So the range is values in gray values, or the domain, sorry. The domain are gray values. And what is the range? The range is a count. So those are set numbers that are positive. So 0. Let's put 0. So this is the way to formalize that. The histogram that is something like this. So the histogram that goes from 0 to 255, and then you have some counts. Okay, so it goes from 0 to 255, and you have some counts, and counts are integer positive numbers or 0. Okay, so that is a histogram. So a histogram is another function. So everything here are functions. And operators, and that is why I said that operators is something more complicated. That's why the operator now. The operator, this one, so an operator is another function. But the argument of an operator is an image. So it takes something that is an image and produces something that is a histogram. So produces something that is a histogram. So everything are functions. See, an operator is also a function. It takes as an argument an image. So this is an image, and it produces as an output a histogram. So everything are functions here. A signal is a function. Operators are functions that operate on functions. You see? Okay. Any question? No. Okay, so let's make a break. Okay, so let's continue. Let's continue. Also. Okay, so next thing is, okay, so we have formalized what is a histogram. Sorry. Then this is just an explanation of what that is. So here is a bit more of the histograms and all that. This plus one is something of MATLAB notation. Okay, so MATLAB starts from 1 to 256. So that means that if you have for instance, the gray value 0, you cannot store it at the location 0 of the histogram vector because there is no position 0. The first index is index 1. And then here in the slides, he's using these plus ones all the times, but I think it is more clear if we forget about the plus one and concentrate on gray values, functions, and so on. Okay, so let's say we have this image, we have this histogram. This is something we already know, and again we take that image, we take that one. And this one is 24 bits true color. So now we know what it means. So just a reminder of what it means is that 24-bit true color means that we have, let's say, red, green, and blue, and we have 8 bits for each one. 8. Okay, and then we have 24 bits, and this is called true color. Okay, so we understand now that this true color is only an approximation because reality, the number of photons coming from each one of the colors is a continuum, so we cannot simply represent it with 8 bits, but okay. Okay, now let's make it a gray image. So now our image will go with, if we use 4 bits, then our image type, the range is set square, so we have discrete locations. And the range now, because we are using just 4 bits, will be 0, 1, 15. This is 4 bits. And this number is 2 to the 4 minus 1. Okay, so let's map our image to something that has only 16 colors. And now what we can see is that, okay, I can decompose this image into different masks. So let's construct the mask of all the pixels that have a value of 15. Okay, so all these black pixels here, they have value 15, and the white pixels do not. Okay. And if I count how many of them have value 16, then there are 603. So that is the count that goes to the histogram. And then I can isolate all those pixels here that have value 14. And then all these pixels, they have value 14, and there are 244 of them. And you can do the same for all of them. So for instance, these areas here that they are in the background, that they are relatively bright, they appear at values 12 and 13, 11. The bag itself, the bag and the legs of the bag that are pretty dark, they appear at level 0, level 1, you see. So we can decompose now our image into layers. Each layer will contain all those pixels that have that particular value. And then we sum how many pixels we see in that layer, and that is the count that we have to put in the histogram. This is that. Okay. So you count how many pixels there are here. That is the count that goes to the histogram for the gray value 15. Okay. Yeah. Okay, so what is the maximum value that you can have in a histogram? Yeah, let's try to be more precise here. So let's say that our image is not, yeah, here I am a bit imprecise in the sense that I'm using here just all the integers that could be negative and positive, and they go from minus infinity to infinity, but simply to represent that we have an image at discrete locations. But if we think of an image that, let's make here, let's have some space. So if we have an image that goes from 0 to r minus 1, so this is the number of rows that it has. And again, here I'm trying to be precise. If you count from 0 to r minus 1, there are r numbers times something that goes to c minus 1. Sorry. So this is simply saying, and again, here there are c numbers. So this is simply saying, okay, you will widen something like this, and r is going from 0 to r minus 1, and c is going from 0 to c minus 1. Okay, so if this is our image, and let's say it is 8 bits, okay, so it goes from 0 to 255. So this is a histogram. So the histogram, sorry, we use a small h for the histogram, capital H for the operator, and a small h for the result. in an exam, I'm not crazy about these things. As long as I understand what you are writing, I don't care. In class, I like to try to be consistent. Okay, so what is the domain of this function? So the domain, it goes from 0 to 55, and it goes to 0, 1. What is the maximum number? What is the maximum value that you can have in a histogram if your image has this size? Which one? Second. So.
This RC.
RC. RC. So in the worst case, all pixels are the same. How many pixels do we have? R times C. So in the worst case, one of the gray values will have RC counts, and all the rest will have 0. So again, this is kind of refinement of what we had before. So what we had before was something kind of loose, saying, okay, we have positive numbers, but if your image has a given size, then at maximum, at most, you can have RC. Okay, good. Then, this is what is explained there. Okay, what happens if we have a color image? So we already know we can construct a histogram for each one of the channels. It doesn't exist the histogram of a color. Okay? So if you have a color with 3 compounds, with 3 components, it doesn't exist the histogram of that signal. It is like it doesn't exist the histogram of a vector. So if you have a vector random variable, it doesn't exist the histogram of a vector, of a random vector. Okay, then we have a color image now, and we here are representing the histograms of each one of the bands, and in black we are representing the histogram of something called the luminance. But for the moment we don't know what it is, but we can understand that it is related to this gray image. So somehow we have turned our color image into gray, and that gray is called intensity, value, luminance. The different names refer to different operations, but in general they all refer or convey the same idea. How many photons are coming from there? Okay. So it is mostly what is the average intensity, not looking at the color. Okay. A very easy way to go from a color image to a scalar and monochrome image is this one. Okay, so you take the 3 channels, apply an average of the 3, and that's it. Okay, so we know there are 3 matrices, so at every location of the matrix, I can take that value and the corresponding value in the other matrix and the other matrix, and I can compute the average. Okay, that average is called the value. Okay, this is the value. Why using 1/3, 1/3, 1/3? Why not using different weights? I could use almost 1/3, much more than 1/3, and much less than 1/3. Why not using these values? And actually, these specific values, they're called the luminance. And yeah, actually, this NTSC, you don't know probably what it is, right? The PAL system, you don't know either. So these were the old television standards to transmit television. So the color standard was NTSC in the US. In Europe, it was PAL. And somehow what it managed was how do I make that two systems can coexist. So at some time, at some moment in time, there were monochrome televisions coexisting with color televisions, and you had to transmit the signal for both at the same time. So the trick was this. So they were transmitting a luminance that was taken by the monochrome televisions, and this luminance was also taken by the color televisions, and then you had to transmit on top of the luminance, you had to transmit the color, and they did it in some way. We will see it a little bit later. The idea there is that we can turn a color image into an intensity image. Doesn't matter if the name is luminance, intensity, value, or whatever. So what we have to do is to combine the three channels. And to combine the three channels, this is a linear combination. And we can come out with non-linear combinations with whatever way to combine them. Okay. Something that will appear later in the course. Why do you think the weight for the green, so they look very much alike, 1/3, 1/3, 1/3, only that this 1/3 is larger and this 1/3 is smaller, you see? We have taken information, we have given more information to the green channel at the cost of the blue channel. Why do you think it is that? Why can maybe more?
It has something to do with the wavelength and the eye range. Yeah, to determine the colors.
Yeah, it has to do with the eye. So how we perceive colors. So we are more sensitive to green colors than to blue colors. Another question is more forward. Why are we more sensitive to green colors than blue colors?
What is the wavelength?
What is that?
The wave.
The wavelength of
green and
blue.
blue.
Blue is around 400. Green, I don't know. It is somewhere in the middle, and red is 700 nanometers. So this is 4. This must be in the middle, and then this is 700. But it doesn't have to do with that. It's something more kind of logical. So think of us as an animal. So what was our environment, our evolutionary environment? It was full of forest. So if it is full of forest, you need to see all the details within the forest. So we are more sensitive to green, and then we are less sensitive to blue. What is blue? Night. By night, we don't see. We don't have enough sensors to see in the night. Some other animals, for instance, mice are night animals, and they have many more sensors to see in the dark than we do. So not all animals see the same. So these weights, so this is something mathematical, very easy, but the way we perceive colors, we perceive more in this way. Okay, then this is math. Okay, the value. Okay, so we take an RGB image, we compute the value. The value is simply the average of the three, and we compute the histogram of the value. Good. Then I can compute the luminance instead of the value. So they look more or less alike. So they have more or less the same information, but not exactly the same information. See that the histogram is very easy. In the image, we also see differences between the two. We have better contrast in the luminance than in the value, you see. Okay. Yeah.
For the contrast concept, is still like the biggest difference between maximum and minimum temperature is the contrast level.
Yeah, so the contrast, I simplified it to maximum minus minimum. It is more complicated than that, but yeah, it is related to that. So it is not only maximum minus minimum, it is, and now you can start to imagine what it is. So it is how many pixels do you have here? So you don't care if the maximum is 51, you don't care if it is 51. What you care is how many pixels you have at 251, and the values around 250, 249. So how many voxels you have here, how many voxels or pixels you have there. So there are many more in the luminance than in, not many more, but there are more in the luminance than in the value. So that is why we have better contrast. Okay, then we have these histograms of red, green, and blue, and this is the value histogram. So the value is the average of the three. Now, this is a proof that, so what is the value? The value is the average of the channels. So would it be equivalent? So if the value is the average of the channels, can I take the histograms and compute the average of the histogram? The answer is no. You see, those are different. So the histogram of the average is not the average of the histograms. And does it sound familiar to you? Do you have any previous knowledge that sounds like that? So the average of the histogram is not the histogram of the average.
It's correlated
With?
and the correlation of the
It is not related to correlation. It is related to linear systems and the commutativity property. So let's expand on that. Okay, so a reminder of what is a linear system. So a linear system, let's say that we have a transformation that is linear and it applies on two signals. So we have x1 plus x2. So T is a linear operator if what? If T holds. And there is a second condition, that is that this also has to hold. So T is a linear operator if when you take two signals and you apply T to this signal and to this signal, this is your response. And then if you scale your input, you also have a scale output. So let's have an example of that. So let's say I construct a system that is, let's put it, I construct a system that takes any input signal and multiplies by 2. This is called an amplifier, right? This is an amplifier. Okay, so let's see if this is a linear operator. So this is our transformation of the input signal x. Okay, so let's see if it is a linear operator. So let's say that I have x1. So x1 is transformed by this function into I1, that is 2x1. I have x2, that is transformed into this. And then I have another one, that is x1 plus x2. And x1 plus x2, that is x3, this is another signal. This this is y3, that will be twice x1 plus x2. But this is twice x1 plus twice x2. And this is y1 plus y2. And this is the transformation applied to x1 plus the transformation applied to x2. So this transformation here, that simply multiplies by 2, is a linear operator. It fulfills the first condition. What about the second one? Okay, so let's say that I have now another signal that is x4. x4 is twice x1. Let's say, or let's not use twice. Let's say it is 3 times. Or in general, it is 8 times x1. So, what about y4? y4 is twice a x1. But multiplication is associative and it is commutative. So I can rewrite this as a times x1. And then this is a y1, and this is the transformation of x1. Okay, so it fulfills the two properties. So this transformation multiplied by 2 is a linear operator. And now you know properties of linear operators. We can represent linear operators as a sequence of transformation. So I have some signal x, I apply some transformation 1, and whatever comes out, I apply transformation 2. And then I produce my output. So I will have here y1, and I will have here y2. And there is a property of linear operators. That is that they are commutative. So it doesn't matter if I take x, first apply t2, then apply t1, I will get the same thing, exactly the same thing. This I2 and I2 prime is identical, only for linear operators. Okay, so what happens, let's say it with our example. So now we have two operators. I have an image. I'm computing, this image has 3 bands. I'm computing the average, I'm producing the value. And then I have another operator that is the histogram. And I'm producing the histogram of the value. Okay. What if I do the opposite? Okay, so this one has, let's represent that it has 3 bands in this way. There are 3 bands coming in, but there is only 1 coming out because the value is only 1 band. Okay, so what if I take first? So I have an image with 3 bands. I compute the histogram. We know that we cannot compute the histogram of 3 bands and compute a single histogram, so we will have 3 histograms. And now we compute the average. The average produces a single one. So this H prime will be identical. What about the average? Computing an average is a linear operator. So let's mark linear operators in blue. So let's say this is a linear operator. This is a linear operator. This is a linear. This is linear. What about computing averages? Computing an average is a linear operator. It is. You can try yourself. Try to do this same kind of proof that I did here for this very simple system. But you can try by yourself. Computing an average is a linear operation. So this is linear. What about counting? Counting is a linear operator. It is not. And there is a very simple proof of that. Okay, so let's say we have a signal. We have an image, let's say, So we have an image that has a value 1 everywhere. So this is the histogram. So the histogram, we have 16 values. So it will be 16 and then 0. 0, 1, 2, 3. Okay, so this is our histogram. What if I multiply my image by 2? So if I multiply my image by 2, so I'm trying to check the second condition. The second condition, if I multiply my image by 2, the histogram should be the previous histogram multiplied by 2. Okay, so let's try that. So if I multiply my input image by 2, then I have 2 everywhere to write all the 2's. And now what is my histogram? My histogram is 0, 0, and then 16 values of 2. This one, so this is histogram 1, this is histogram 2. So now the question comes. Histogram 2 is equal to twice histogram 1. It is not, because twice histogram 1 is this map here, like goes to 32. It goes to 32, and these two are not equal. So computing a histogram is not a linear operation. So counting in general is not a linear operation. So this is not a linear operation. And if it is not a linear operation, I cannot apply this idea that I can commute operators. So the average, so the histogram of an average in general is different. So these two things are different from the histogram of the average of the histograms. So you know already a lot of these tools. You know the bricks, but you don't know how to construct with those bricks. But it is very important that you learn to think about what is a linear operator, what kind of operations I can do with linear operations, what are functions, what are signals, what are all these kind of things that for the moment for you they were just mathematical problems, but they are really, really useful. Next. So now we know that we cannot compute non-linear operators, and computing a histogram is a non-linear operation. Okay, so this is MATLAB. We don't care about MATLAB. Okay, now, what I can do, let's, so we said here that a histogram, we had it somewhere here. So histogram is simply counting. Okay, so what if and we knew, for instance, we knew that the maximum value could be only RC. What if I construct a new, so once you have the histogram, you normalize it. Okay, so now we will construct a new histogram, H prime, that goes from 0 to 55. But now instead of 0, 1 RC, it will go 0, 1, 1, and this is divided by RC. That is, this is not divided by RC. So that is, H prime is H divided by RC. I normalize the history. So now it goes from 0 to RC, from 0 to 1. And it has a property. that is if you take, let me make it blue. If you take H prime, what is the argument? The argument is a gray value. Okay, so let's write now the argument explicitly. And I sum all these gray values from 0 to 255. What will be this sum? This is equal to 1. Let's see why. Maybe the answer is in this little bar. This little bar. This one. Okay. And let's make it this one. Okay, so what is this layer? This layer is how many pixels have value 15. How many pixels? Sorry. How many pixels have value 15? How many pixels have value 14? How many pixels have value 13? So if I sum how many pixels have all these values, what do I get? The total number of pixels. Because a pixel, either it has value 0 or 1 or 2 or 3 or 15, but it needs to have one value. So if I sum all of these numbers, what I get is RC. So now, if I divide all these counts by RC, and I sum all of them, the addition has to be 1. Okay, so that this H prime that is normalized is something that is called the PDF, probability density function. And this is something you are familiar with. Can you tell me a PDF, a very famous PDF? You're familiar with PDFs of discrete variables, discrete random variables. Tell me one.
Binomial.
The binomial. The binomial is one. Even simpler than that. What is the PDF of throwing a coin and getting a head or getting a tail? So I have here result of the coin. I have here head. I have tail. And this is 1/2. And this is 1/2. This is the PDF of this coin. This is the PDF of throwing the dice. What is the PDF of throwing the dice and getting any one of the faces? So face 1, 2, 3, 4, 5, or 6. All of them have the same probability. Write only one of them. That is 1/6. Okay, so now the probability, suppose that this is normalized to 1. Okay, so we divide by RC. What is the probability that I take a pixel at random? So I take any one at random, and it has value 0, and it has value 1, and it has value 2. You see, this is that PDF. If you take a pixel at random, the most likely result is that it has value 12. There are many more pixels with value 12 than with any other value. So the histogram is an approximation, not an approximation. If we consider it to be a discrete random variable, it is the PDF of that discrete random variable. So you take a pixel at random. What is the probability that it has value 12? What is the probability that it has value 11? That is H prime. So H prime is this one that is normalized. This is the PDF of taking a pixel at random and having that value. Okay, we have moved into the domain of random variables. That is something also that you know, that is cumulative density variable, CDF. Okay, let's make it red. So CDF, cumulative density variable, density function. Okay, what is the CDF? So the CDF, okay, what is the PDF? The PDF is the probability. Now let's define the random variable I. We are abusing a bit the notation, okay? So we are abusing the notation. So we say PDF of the PDF can only be computed of random variable, but now our image will be a random variable. The random process is simply taking a pixel at random. Okay? We are using the same letter, I, for the image, that is was a function, and now for this random variable, that is taking a pixel at random from the image. Okay, so what is the PDF? The PDF is the probability of having a particular gray value. Okay, so what is the CDF? So the CDF, so PDF is a function whose argument is D. So it is the PDF. You can also write it like this. Okay, so it is the probability that the image I takes the value G. Okay, so what is the CDF? The CDF is some kind of similar definition, but now instead of equal, it is smaller or equal. And we can write it in this way. So it is a function of G. So given a gray value G, what is the probability that the taking a pixel at random from the image I, it takes a value that is smaller or equal to G. And we know that there is a relationship between the CDF and the PDF. So what do you have to do? You simply have to sum, or you have to go the sum from G prime equals 0 to G of the PDF of I prime. So if I want to compute what is the probability of being smaller than 12, what I have to do is what is the probability of being 0, 1, 2, 3, up to 12. Sum all those probabilities, and I will have the PDF of that image. So for instance, here, what is the CDF of the dice? So the CDF of the dice, maybe let's make the axis black. So another CDF. So, what is the probability that a dice has a value smaller than 1? So 0.5, 0.6, 0. And the CDF is like this. A smaller or equal 1. So at 1, exactly at 1, it has a home, and then it goes up here. And then it goes by steps. Might goes to 1, what is the height of these steps? 1/6. Okay, so this is the CDF of the dice. Okay, I can do the same, but now instead of dices, I can use images. I can take this normalized histogram, I can add, and it will go up to 1. And that we will call this, during the lectures, we will call this H prime. Sometimes we don't distinguish H or H prime, but today this would be H prime, this would be H prime, and this would be H prime. Well, we remove the prime. So the CDF, typically you use capital letters, and for the PDF you use small letters. Okay, and the prime simply is to emphasize that it is normalized. So the standard histogram is not normalized, it is simply counting. If you normalize by the number of pixels that you have, then you have the normalized histogram. And if you integrate or sum this normalized histogram, you have the CDF. Okay, so that is what is in these slides. I particularly the way it is presented, but those are the same ideas. So this A is the total area, that is RC, and this total area can be expressed as the sum of all the PDFs. These are not PDFs, they have not been normalized. And here we have some representations. Okay, so yeah, here you have the same kind of equation that we had before. And what about the rest of the equations? Okay, so let me see what time. We have 4 minutes. Okay, so let's say, so we know how to go from the PDF to the CDF. I simply have to sum. Let's do the opposite. Let's say that you know what is the CDF. So you are given H of T, and you want to compute H prime of T. This you know. How would you compute that? Let's make it.
Derivative equation.
Sorry?
Derivative.
You?
Making the derivation.
Derivation. Differentiation. Almost there. We are with discrete signals. So for the moment, G is discrete. Okay, so G takes the value, so the gray value takes the value 0, 1, 2, 3. So if it is a discrete signal, you cannot differentiate. Okay. But it is almost there. It is the equivalent of the differentiation, but for discrete signals. But it's this one. H of T minus H of T minus 1. This is called the first difference. Do you remember that system? And this first difference, it makes a lot of sense. So the CDF is summing all the values up to G. The CDF of G minus 1 is summing all the values up to G minus 1. So what is the difference? What is the last term that I have added? So it is all of them up to G minus all of them up to G minus 1. And like that, you can recover from, you can go from this function to this one. Okay, good. Then, yeah, as Imani said, this is for discrete signals. What happens if we have continuous signals? So if we have continuous signals, let's say that I have something like this. This is the PDF. D. This is the axis D. And what is the integral of that? So the integral of that will be something like this. So it will be 0 up to here, and then it integrates and it goes to 1 asymptotically, and it reaches 1 at some moment. This would be the CDF of D. What is the equivalent for continuous signals? So the CDF is the integral from minus infinity to G of the CDF D prime differential of D prime. And if I want to go back, it's the opposite. I have to differentiate. The CDF of D is simply the derivative of the CDF of D with respect to D. And now you recognize these relationships between discrete and continuous systems that you already know, but probably you don't have all of these together in your mind. So these two operations are complementary to each other, are the opposite of each other. And these two operations, this one and this one, are the opposite of each other. And they are the equivalent. So integrating the equivalent in discrete signals is summing, and differentiating the equivalent of in discrete signals is computing the first difference. Okay, enough for today, I think. So let's stop here and